Okay, good morning, everyone. So this is the lab for week 3. So if you go to Moodle, you go to lab week 3 linear system, you will see that there's a problem here. So lab week 3, okay. And so I'd say that you have to solve a to the mx equal b, okay. And you try to solve it in 2 ways, okay. Well, first you use LU factorization. And secondly, you use just standard Gaussian elimination. And then you measure the time. Okay, you measure the time difference. So that is the whole purpose of the lab today. Okay. And so we do it step by step. Okay, so let me, so you can read the problem here. But first, let me explain roughly what we are trying to do. Okay, so let me explain by sharing the whiteboard. Okay, so you can see the whiteboard, yeah. So what I want to do is I want to I want to solve this a mx equal b, right? But it's not recommended you compute the power of the matrix, okay? But you solve it like successively. So let me illustrate. Maybe suppose I take m to be 3, okay? And you try to solve, there's some question in the chat box. I can't see what you are writing. So you cannot see my whiteboard. Okay, so now let me try it again. Share the whiteboard. So now can you see the writing now? Or? Okay, so you can see the whiteboard, but no writing. Okay, so let me start writing again. Yeah, that's all good now. Okay, so maybe the network is a bit laggy. Yeah. So everything is good, yeah. So now suppose I try to solve a to the m x equal b, and suppose just take the simple case m equal 3. Okay. Then what I try to solve is I try to solve a cube x to be equal b. Yeah. But I instead of solving a cube x equal b, right? I try to solve like ax1 equals 0. Sorry, ax1 equal x0, but x0 is defined to be the vector b. Okay. Then so this is the first step, yeah. So the first step, and then the second step is I try to solve a x2 equal x1. Okay. So you see, the first step I got x0. Sorry, x0 equal b. The first step I got x1. Yeah. And then the second step I got x2. Right. And then the third step I solve a x3 to be x2. Okay. And I stop here. Yeah, I stop here. I claim that x3 is the solution of the original equation. Okay. So why is that? So now, claim is x3 solve So original equation. Okay. So now why is that? So now suppose you got AX3. Then by step 3 it equal X2, right? Okay. And then now if you multiply A on the left and on the right, you got A square X3 equal AX2, right? But so this one is by step 3, yeah. But you see AX2 equal X1 by step 2. Okay. And then, okay, so now if I multiply A on the left and on the right again, then I got A cubed X3, okay, equal A square X2, but then it equal AX1. Okay. And AX1 is just equal X0 by step 1. Okay. And X0 just equal B. So essentially A cubed X3 equal the vector B. So that is what you want, right? So from the beginning. So why we are doing this? Okay, you will see that eventually you will see that, you know, I mean, if you compute, so there's two ways, right? You can compute A cubed directly, right? Then you solve, you know, like A cubed X equal 3 by Gaussian elimination. But then in this way, you don't have to compute the power of the matrix, okay? And you will see that computing the power of the matrix is very costly. So that's why it is recommended to do iterative like this. Yeah. So you get the idea, right? So this is m equal 3, but then you can set m to be any power. Yeah. So now in summary, if you go back to the question, okay, so now we look at the algorithm again. So you look at the algorithm again, okay? So first you define X0 to be equal B, yeah? And then you solve AX1 equal X0, AX2 equal X1, and then AXM equal XM minus 1. And finally, you define the solution to be XM, right? Yeah. So you see, so this one, you have to implement a loop here, the loop here to solve M linear systems, okay? So now it boils down to the fact that you have to solve M linear system again and again, right? With the same matrix A, yeah? And now, so now we will try to do it step by step, okay? So now we did the step, convince yourself that X obtained from the above algorithm satisfy AMX equal B. So this one I did for M equal 3, but you can follow similar steps and you can show that it is true for any M. You know, you can show it by similar process, okay? So first you have to download LU solve from Moodle. So if you go back to this, I just put LU solve here. So you download LU solve, and then this LU solve will solve the. So now if I share my MATLAB, so I share my MATLAB, and then you will see that. You see my MATLAB, yes. So now I have to copy LU solve from the previous directory into this directory. So I have to check whether I have that LU solve. Okay, so maybe 3. Yeah, so is the difference between LU factorization and using A when you use LU factorization step in the loop. No. It's a bit more than that. You have to use A equal LU. Well, I will show you step by step. Okay, you have to compute L and U, and then you have to solve. I mean, in two steps, Ly equal B and Ux equal Y. So maybe we just do it step by step. Okay, so there's some difference. So there's like when you use LU factorization, you have to do 3 steps instead of a single step. Okay, so now let me try to show you the step. Yeah. So now what I want is I want to copy the LU solve here. What happened? So lin. Okay, so then I have to copy LU solve here. Why I cannot copy? Maybe copy. Strange. Okay, so I have to move. I have to move the LU solve here. Copy it into okay, so I have LU solve here. So you can edit LU solve, you can open it, LU solve. So LU solve is essentially it takes in a matrix L, matrix U, matrix P from the LU factorization. Okay, and then it takes in the right hand side of the linear system, and then it just use the so the L and the U matrices and solve it to get X. So this one is just checking the size of the matrices, and then it solve like X equal solving like solving matrix. So this part, so there's 2 steps, right? You have to solve. So this part is you just solve L X equal B, right? So remember, so actually, this is the first step, and then after that you solve Ux equal, well, actually, because this one, the variables is X, but you reuse it, so maybe it's clearer to get this one is Ly equal B, and then you solve Ux equal Y, yeah? But the variables X is just reused, has been reused twice. But anyway, so this one is how you use it. You just give the, here, you just give the L and U then a P, and then you give the right hand side, and then you get the vector X, okay? So now what we are going to do is, so you, well, this one is just, lazy in the making a new variables. You can make a new variables, so you can make this one to be Y. I mean, and then you can make this one Y. Okay, that is still the same. Okay, yeah. So I mean, sometimes like if you program a bit like carelessly, you can reuse the variables when you don't use it anymore. But anyway, so it's not a big problem. Once you understand what is going on. Yeah. So then, okay, now I just fix it. Okay, so now you go back to your script and you say that, okay, now I want to, so the first step is you download the LU solve, right? The second step is you read and understand how LU solve works, and you did it already. And you can type help LU solve. So help LU solve. And you see, you can see that solve AX equal B, and using PA equal LU. And then first you have to solve Ly equal PB, and then after that you solve Ux equal Y. Okay. So now we go back to the problem. So the problem say that now run LU solve. So run LU solve. So this one you say that this one is the script is run LU solve. Okay, so we name the script like this. And now the first step is you prompt the user to enter the value for n. Okay, so now prompt the user value of n. Yeah, so remember we use this command again and again. So size of the matrix A. Okay, and you say that n equals something, and you let the user n to enter. Okay, and then part B is you prompt the user to enter the value for m. Okay, so you do the same. Enter value of m. So m is input our m equal something. Okay, and then once you got n and m, now you have to do the solving. So use MATLAB ran to generate a random square matrix. So you just look it up. Okay, so see, maybe I just cut and paste the question here and you will see it. So okay, so you just use, so A is random. So this command just give you so you can check, yeah. So random 3 will give you a 3 by 3 matrix, and random n is a n by n matrix. So random values. Okay, and then the next one is add n to the diagonal of the matrix A. So how do we do this? So how do we add n to the diagonal entries of matrix A? So this will make sure that A is invertible. So there's a theorem in linear algebra say that if the diagonal entries of the matrix is much bigger than the off diagonal values, then the matrix is invertible. Okay, so how do we add the diagonal entries? Okay, so remember the diagonal matrix. Well, it's just an identity matrix, yeah. And you can multiply by n to the identity matrix. Then you got the diagonals elements. Each of them is n, right? And you just add it to the matrix A. Okay, so now let me run it first, yeah, to see whether it works, yeah. So now we we label this is run LU solve. So run LU solve. Okay, so you see that if I run it, so I got say n equal 4, power is 3. So I got a matrix A like this. Okay. So now the next step is, so now what is the next step? So the next step is I try to okay, so this one is exactly, you just cut and paste from the question. So find the LU factorization of the matrix A by the command LU. And then you compute the CPU time for this process. Okay. So you just cut and paste part E into, I mean, this, the 3 commands here. So part E here. Okay, so this one, so if you help CPU time, so what it does is it just get the CPU time in seconds. Yeah, so inside the CPU there's a clock, and whenever you call CPU time, and it just read the clock for you and put in the variables t. Okay, so you see, suppose now you read the clock from CPU time, let's say that 10:22, 00, and then you do the LU factorization, right? And then you read the clock again, right? And it will be say 10:22.50. Then you take the difference, and then you get the time has been used by the CPU. Okay, and then this one give you the LU factorization of the matrix A, right? So this command compute the LU factorization of A. So remember, P is a permutation matrix, and L is a lower triangular, U is an upper triangular matrix. So we have to give on 3 outputs. Okay. And now use MATLAB to generate a random vector B. Okay, so now you have to use, actually you have to compute the time for, maybe say that LU time is just T1 minus T0. Okay, so this is the time taken to compute the LU factorization. Okay. So far so good, right? So now how do I generate the random vector B? So we use a ran command again, but you see, look, the ran command, how do you use it? If you ran with only 1 parameters, then it gives you a 3 by 3 matrix, for example. But if say ran 3,1, then it gives you a 3 by 1 matrix, where it's just a column vectors. Okay, so this is exactly what you want to do. So B will be a vector with n rows, 1 columns. Okay, and now you got the matrix A, you got the vector B, and now we have to implement our algorithm. So now you have, so remember, now I go back to the algorithm. Yeah, so or maybe let me cut and paste. Yeah, so this is the algorithm here. So now we have to implement the algorithm here. So implement the following algorithm. Okay, so now you have to define x0 to be equal b, and then you solve ax1 equal x0, ax2 equal x1, axm equal xm minus 1. Okay, but now I don't want to save x1, x2, x3 up to xm. It's just a waste of memory. I can reuse the vector x again and again. Okay, so this is, I mean, it's not like, it's not important to save on the vectors. Yeah, you can reuse, like x is an empty box, right? So then you can put the values of x0 there, then you throw it away, you put in the value of x1, and then put in the value of x2 and again, right? So that is what I want to do. So I want to reuse the vector x again and again. So x0 to be equal b, so I just say that x equal b. Okay, so now I say that x equal x0 equal b. Okay, so this is the first step. And now how do I implement this? So you know how many times you have to solve this? How many times? M times, yes. So we should use for loops or while loops. For loops, yeah, because you know the number of iteration. You just say that for say k from 1 to m, right? So you have m iteration. Okay. So now in each iteration, yeah, what are you going to do? So now you say that you solve well, remember, here you have a running variables. Yeah, so maybe say solve ax1 equal x0. Okay. And so remember how we use the LU solve. So LU solve. Help LU solve. Yeah. So actually this one, if you read the question, this one say that you use LU solve to solve this, and this is exactly what I'm going to use. Yeah, so LU solve. Okay, so I say that x is LU solve. Okay, and then remember L we have computed already, right? In line 12. Yeah. So now I just put in L, and then I put in U, then I put in the permutation matrix, and I put in the vector B. But remember, actually the vector B, the right hand side is x0. So x0 here and x1 here. Okay. But remember x0 just equal x. So actually this one is just x. Yeah. Okay. But you see x1. Okay, now, once you solve this, then you don't need the values inside the vector x anymore, right? Yeah. So I just reuse x. So I just make this one to be x as well. Okay. So what it does is, first it uses the variables x, what inside the variable x, and solve to get a vector x1, but then it got the values and it put in the vector x again. So you reuse, so this one is how you save the memory. Okay, so it doesn't look like mathematics, yeah, but it look like a programming language. You just, this one is not a equal sign, but like you assign the values into the the variables, you know, so you reuse it. So this one we reuse the vector x. Okay. And so now we can run it. So you see, so this one at the end of this loop, then you got xm, you know, so in the end, then you just got x is the solution. So here, after the loop, x is solution of a to the m x equal b. Okay, so you can check that. Yeah. Okay, so now we run it. So let's see, we run it and see whether it works. Yeah. So suppose I have, so in just say 4 by 4 matrix and power just 3. Okay. And now you check. Yeah. So what is b? So you got b is here. Okay. So what is a to the 3 times x minus b? Okay, and we can check the norm of this a to the power 3x minus b. And you see it close to 0. So this one is like 7 times 10 to the minus 16. So close to 0. So x is a solution of a cubed x minus b. Okay. So by solving this. Yeah. So remember we discussed this, you know, before we implement this. So, you know, you can save all the vectors, but it's just a waste of memory. You can save x1, x2, xm, you know, but just a waste of memory. We just reuse the vector x again and again. Okay. So does it make sense? So any question about this one? Okay, so it's good. Okay, so now, you know, now suppose I want to measure the time. So if you look at in the question, so let's say that use the for loops to implement algorithm 1. In each step of the loop, use 2 methods to solve ixi equal xi minus 1. So lu solve and backslash command. So con x is a solution given by lu solve, and con y is a solution given by backslash command. Okay. So in the loops, you compute the lu time and the ml time, the CPU time used for each method. And the hint is you don't have to define the array y1, y2 up to ym. You can reuse variable y. So y equal a backslash y. Okay. So now I just have one more command. Yeah. So now instead of solving this by LU factorization, so this one by LU factorization. And now I can solve a x1 equal x0 by backslash command. Yeah. Backslash. So now what command should I put here? So what command should I put here? So anyone, what command should I put in this line to use a backslash command? Yeah, y equal a backslash y. But now, what is y? We haven't defined y0. So this is a problem. So where is y0? Yes, so y0 equal b. So you have to put in y equal b right here. Okay, so y equal y0 equal b. Okay, and you can run it if you run it. So say for here, okay, and you say, so what is the norm between x and y? Oh, equals 0. Okay, so x and y are the same vectors. Okay, now, yeah, out of the loop, yes. So after the loop, then y is a solution of the solution of AMY equal B. Okay. So now why bother? So now you see, now we come to the question, why bother to solve the linear system by LU factorization? Okay. And so now the next step is you measure the time. You measure the time. So remember, so this is how you measure the time. Yeah. Okay. But here you measure the time only for the LU factorization. But now I want to measure the time for, you know, solving by LU factorization and solving by backslash command separately. So how do I do that? So how do I compare the times taken by the two methods to solve A to the mx equal B? Make the variable outside the loop, yes. Yes, okay. So tell me what variable you want me to put outside the loop. Okay, so what variable we should put in? Say, so in the, let's say LU time and ML time. So LU time. Yeah, but I mean, we can follow the question say that, okay, so there is, we can set two variables separately. But actually LU time, you have it already. So LU time is the time taken to compute the LU factorization. So we don't have to define LU time again, right? But now we have a ML time equals 0 initially. So this one is the time for backslash command, yeah. Okay. So now how do we do this? So now we will put in the time here. So remember, this is the way you take the time, yeah. So for the backslash command, so I got T0 equals CPU time. So again, you know, C0 and T0 and T1, you just some variables, you reuse it again and again, right? So this one is CPU time. So now how do I add the time? So how do I add the time? So give me the command to add the time. Anyone give me a command to add the time to the backslash command, so the total time. Yeah, so ML time will equal ML time plus T1 minus T0, right? Because remember, you know, I mean here you look at the clock, right? And you do the backslash command and you look at the clock again. And you have to take the difference in order to find out the time, yeah? And then you add to the total time. So now you do the same for the LU solve factorization, right? So now I I can put here, so T0 equals CPU time. And so T0 and T1, we just reuse it again and again, okay? So CPU time. And then you add, so ML time, sorry, LU time. So, you know, LU time, you don't start with 0, but you start with the time, you know, it computes the LU factorization, and now you add on the time it's solving the linear system, right? So you just add on. So T1 minus T0 as before. Okay. And now we run it. So we run it. So now N is say 5, power is 4. Okay. And now ML time. So it's very fast. So we cannot see the difference. So it equals 0. So maybe let me increase the, so suppose we take N is 100, yeah, or maybe 1,000, and M is 6, still very fast, huh? So ML time, you see, now you see ML time is non-zero, right? Because the computer is faster and faster these days, you know, so, and then LU time, you know, so there's some difference, okay? But now let's see, look at the next question. So check whether, at least we've done the question G, yeah? So you check the time, you check the time for both methods, and then check whether both methods give the same answer. Okay, so okay, so now check whether, I mean, you can read it, yeah. So this one is part H, and so there is the formula for you to do that. So you check the norm, so infinity norm, and if it's less than 50 epsilon max of infinity norm of x and infinity norm of y, and epsilon is the machine epsilon, then print on the screen. Both methods give equal solution. Okay, so now how do we do that? So if, okay, and then you say that norm of x minus y, you put in infinity norm, okay, less than or equal max of actually 50 time epsilon time max of norm of x infinity. So this one is, I just translate the formula in the question. Okay, so if you look at the, the question again, yeah, so if you look at the question again, yeah, so I just translate this inequality. So the norm of x minus y in infinity norm less than or equal 50 epsilon max of the infinity norm of x and y, then you print out this message, okay? Otherwise, you print out this message, okay? So you see, you use a command, this norm v infinity, okay? So then, okay, so now I go back to the screen of MATLAB. Okay, so I compute x y infinity. Yeah, and so it's a bit lengthy condition. Okay, and then if this is the case, then you print out the message. Okay, so both methods give equal solution. Yeah. Else f print f. You know, you can print out another message. Yeah. So okay, so this is the message. Okay, so now we run it again. We can run it again to see whether it works. Yeah. So say n is 100. Sorry, maybe 100, and n, so m equal 3. So you see both methods give equal solution. So you use LU factorization or you use backslash command, so it still give you the same. So it could be 1000 power 6. See, so both methods give equal solution. Okay. So that is the question H. And then the next one is you print out the time. So print out the, so how do I print out the time here? So how do I print out the time? So how do I print out on the screen? So this is H, this is I. Okay, so there is someone use fprintf. Yes, use fprintf and %f. Yes. So now, well, first we have to print out, you know, so we have to print out something like this. So now this one is the example how you should print out. Yeah. So example is like this. Okay. So you will say that, okay, now I will say fprintf, and I take the message here. Put right here. But you see, now you don't want n is 2000 and m equal 20 again and again, right? We want to print out according to our value. So we put in the value %d. So %d for decimal, %f for float, %d for decimal, right? So this one, the first slot here, you say that I want to put in the values of n from my inputs. Yeah. So I put n here. And the second one, you know, this %d is the m come from my input. So I will put in m here. Okay, so fprintf, remember, so there's two ways to use it. One is just give a string and then print out whatever it is given inside the string. Okay. And the second way is you want to print out the values of the variables. Yeah. Then you can specify the format of the print out as well. So this one, I want to print out n as a natural, as a decimal number, and m is a natural number, so I want to print out as a decimal number. Yeah. So I put in the %d, you know, to make sure that it print out as a correct position. Okay. And then I give the variables n and m, so then it will print out exactly those values. Okay. So then the next thing is I say that fprintf time you know, time, whatever it is. So time when using LU solve. Okay, and I say that is equal percent F second. And then now I give the variable name. So this one is LU time. LU time. Okay. And do not forget to close the string. Okay. Otherwise, you see there is some, you know, incorrect colors. Okay. So percent F is just like print out a floating point numbers here. And the values come from the variable LU time. Okay. And you can do the same for the next line. Okay, so essentially it's the same here. And you do the same here. So you say this a percent F. So backslash n just means that's a new line. Okay. And this is ML time. Okay. And now you can run it. So now you run it. So say n is 2000 and m equal 20. So you see, when you use LU factorization, then it takes only 1.1 seconds. Yeah. But if you use a backslash commands again and again, 20 times, like 10 seconds. So you say 10 times longer than use LU factorization. You see, so that's why LU factorization is a preferred method when we try to solve a linear system again and again. Okay, you know, you can try, you know, say different case, say 4,000 by 4,000 and power is say 25. And now it's a bit longer, right? You see, so LU solve only about 8 seconds and backslash command 88 seconds. So 11 times slower than using the LU solve. You see, so LU solve factorization, make it faster. Yeah. Okay, so let me try. And so you say that if n is 100, yeah, and m equals 6. Well, actually, you see, in this case, because n is so small, you know, very small. So then you see that the backslash command is faster, yes, because when n is too small, you know, maybe computed the LU factorization, the time is too long, right? But, you know, I mean, for n big, you know, we have to say that for n big enough, say for n bigger than 1,000, then LU factorization will speed up the process, okay? But for, you know, I mean, for things small like this, you see that, I mean, well, people interested only for the big n, you know, suppose you have like a few thousand or n is a billion. So in engineering application, you know, I mean, n should be very big. Yeah. So for small n, then you will see that, you know, sometimes backslash command could be faster. I agree. Yes. So does it make sense? Okay. So we just say that it's faster for big n. And, you know, we will study that topic in the next lectures. Yeah. So can you explain why? Okay, so we have to wait for the next lectures. Yeah. So now next lecture will explain why the LU factorization is faster for big N. Okay. And so the next one, I think the next question is, so now if you go back to the question. So we've done this part, yeah, and the backslash command is 15 times longer than the LU solve. Okay, so this one is for big N. Okay, and can you explain why? So we will explain it in the next lectures tomorrow. Okay, so work out how many bytes MATLAB needs to store a 4000 by 4000 real matrix. Yeah, and so remember, one entry takes 8 bytes. Okay, and so 4000 by 4000, you know, then you got 4000 square multiplied by 8. Yeah, and then, you know, you can check your answer. So now suppose I have, and what happened if you want to store a complex matrix? So now suppose I can check it in MATLAB. Yeah. So now if you take a 4000 by 4000 matrix, yeah, you got 4000 square entries, you multiply by 8. Okay, so then you got 128 well, so 128 million bytes. Yeah, and we can check the answer by, suppose I set A to be a random matrix, 4000 by 4000, and I check A. So you see, so it will be exactly what we expected. Okay, so 4000 by 4000, and it takes 128 million bytes. Yeah, but what happens if you store a complex number, sorry, complex matrix? So you see, if you make a complex matrix, then you say that, okay, random 4000 by 4000, and then you have to add I is the complex unit. Okay, 4000 by 4000. Oh, sorry, I should break it. So you see, if we don't put a semicolon at the end, it just print out every entries. Okay, so you see now, now how do we check how many bytes does it take? Well, so one complex number, you know, there's a real part and imaginary part. So it takes 16 bytes, yeah. And then 4000 square entries. So it will be that much memory. And you can check, yeah, so it's exactly this number of bytes, yeah, 256 millions. Okay, so I think we have to stop here because it's 11 o'clock already. So let me stop the recording and see whether you want to